Hello and welcome to our video about naming binary ionic compounds, and this is part 3 where we're going to add in our very last rule in this series for the ionic compounds. Now this won't be the last rule we see for naming, but it will be sort of for our first half of naming compounds. So let's get into what transition metals are and why they're different to name. Now we have named quite a few binary ionic compounds so far in this series. We started by just sort of with these first two rules where we had the element name for the cation and then our root plus IDE for the anion. So if we had chlorine, it became chloride and so forth. In our last video, we added in the polyatomic ions. We looked at some of the polyatomic ions, we looked at what they were, and we talked about how we would name those if they were the cation or anion. Now our very last rule is down here, and I've been crossing it off in the previous video saying that we're going to get to it in the third video, and so now here we are. Now, if we have a transition metal, those have more than one possible charge for the cation. Now, transition metals and metals in general will tend to form cations. Now, they'll tend to form cations, and in the case of their transition metals, they can maybe form more than one possible charge. Now there are some exceptions. There are some transition metals that only have one charge, and there are some other things that do have more than one possible charge that aren't a transition metal. But when we have something that has more than one possible charge, we have to put it in the name what the charge of that metal is in that compound. So essentially what we're doing is when we're naming it, we're telling someone else, this is the metal cation that's in this compound. So for example, lead can have two possible charges. It can be +2 and it can be +4. If we have a compound with lead in it, we need to let someone know if we're talking about lead-2 or lead-4. And so that's what the Roman numerals are. Now, just as a refresher for the Roman numerals, if we have a Roman numeral of 1, that is just going to be an I. 2 is going to be II. 3 is going to be III. And 4 is going to be IV. Now, we could keep going with these, but for this video, we only need 1, 2, 3, and 4. When we're going through these, I'm going to point out our transition metals. We're going to look at a couple of common ones we might see. What I'm not going to do is I'm not going to put up the table of transition metals and all of their possible charges. Today I'm going to talk about how you would figure it out based on a compound. There are many, many tables, including tables in textbooks, that tell you for all of the different transition metals what the possible charges are. Today we're going to talk about how you would calculate it based off the compound. I have the periodic table here. We have the transition metals right here in yellow. Now these are going to require us to put some Roman numerals on our name in order to distinguish between the different cations that they could form. Now there are some that don't need the Roman numerals. There's 3 right here. Zinc and cadmium are going to form a 2+ ion, so those are all going to form a 2+ ion. We generally don't put it as zinc 2. We would put cadmium. That generally forms a 2+, and silver forms a +1. Now, I'm saying generally because there's always exceptions to these rules, but the vast majority of compounds that have silver, zinc, and cadmium are going to be the silver +1, zinc 2+, and cadmium 2+. So we tend to not note that those are the charges used for those 3. Now for the other transition metals, we will note the charge. Let's do some practice. So we have COBr2. Now we can probably figure out the second half of this pretty easily because we've named other bromide-containing ions before. Bromide ion-containing compounds before. And so Br2 is just a bromide ending. We take bromine and we turn it into bromide. We've seen that pretty extensively in part 1 and part 2. The cobalt is where we're adding a different sort of rule. Cobalt is right here. I just boxed it in our periodic table. Now, in the case of cobalt, we're not really sure what the charge is, but we can figure this out from what we know about the bromine. We've actually talked about what bromine is in some other videos about ions, but bromine is right here. Bromine has 7 valence electrons. Now, bromine has 7 valence electrons, and to get to its 8 valence electrons, or to have a full octet, it's going to gain 1 electron. And when it gains 1 electron, it is going to form the bromide ion, which is Br-. So the name that we would call just the Br- is a bromide ion. The anions get that IDE ending, and that's why we call the second half of this name bromide. Now in this case, we see it says Br2. So we actually have 2 bromine ions right here. Now what I like to do sometimes is draw out, and I'm going to erase this really quick. I like to draw out what I'm talking about with some pluses and minuses just to see what we're talking about with charges. We have a cobalt here, and there's only one of them. And we have 2 bromines. It says Br2. For each of the bromines, each bromine is coming in with a negative charge. Because they are not coming in as a neutral bromine, they're actually coming in as bromide ions. They are gaining an electron. Now, remember back to when we talked about electrons and being transferred in ionic compounds. I had said something along the lines of those electrons aren't appearing out of nowhere. Something is giving those electrons to the anion. And in this case, the cobalt is giving those electrons to the bromines to form bromide ions. In this case, if cobalt is giving away 1 electron to one bromine and another electron to the other bromine, this must have a 2+ charge. Our charge is, and since this is neutral, we don't see any charge on the COBr2 right here, this must have a 2+ charge. So in this case, this is telling us that the cobalt is cobalt 2+. Now the way that we name that, we write cobalt, parenthesis, Roman numerals for 2, so we would call this cobalt 2 bromide. So what we're doing each time is figuring out what the charge for the transition metal is, and then we put it in parentheses with the Roman numerals. This is allowing someone else to read what we wrote and know that we're talking about the cobalt 2+, and they would be able to take our name and get back to this formula. And so we need to give whoever's reading this name enough information to know which compound we're talking about. Now this compound is combining what we learned in part 2 as well as our transition metals. So we see we have Fe here, and that is right here. We have iron. Now we don't know what the charge on iron is, but we can figure out what the charge on the SO4 is. So the SO4 here is, we come down here, it's sulfate, and sulfate has a 2- charge. Now, unlike that last example, we actually only have 1 sulfate. Remember, we had 2 bromide ions in the previous one. We only have 1 sulfate, but the sulfate has a 2- charge. So if I write this right here, our sulfate has a 2- charge. I sometimes like to put these in little bubbles so I can see visually what's going on when I'm doing this on the screen. So our sulfate has a 2- charge. Now again, those minus charges, when we're talking about things, when we're talking about transfer of electrons from a monatomic ion, they're getting them from somewhere. In this case, the iron is going to have a charge, and it's going to be attracted to this SO4 that has 2-, and it's neutral overall, and in that case, this one must be 2+. So we see that this is 2+, and there is only 1 iron. Now that's important that there's only 1 iron. If there were multiple iron, we would need to account for the multiple iron in this charge right here. But the FeSO4, that is neutral, so let's figure out the name of this. Now we know the Fe is iron. We have iron, 2, because that's the charge, and then sulfate. And so it's iron 2 sulfate. Let's look at a slightly different example. So this one was a transition metal with a polyatomic ion, and we had 1 of each. Here we have iron, but this has a polyatomic ion of, and we'll come down here, and we have an OH-. So this has a hydroxide ion on here. and it actually has 3 hydroxide ions. Now in this case, we see our iron. We know that's one of our transition metals right here because we've seen that. Now in this case, for our OH minus, there are 3 of them, so I'm going to draw this out here. Fe, and then we have 1 OH minus, 2 OH minuses, and then 3 OH minuses. Now in this case, because this is neutral, this must mean that that iron has enough charges to cancel out all 3 negative charges. That means that our cations must be a 3+. In this case, there's only 1 cation, it's 1 iron. So that must mean that this is iron 3+. The way that we write this is iron III hydroxide. So you'll see it's not much different than naming the other ionic compounds, but there is this extra step. We have to figure out what the charge is. Now in all of the examples we've looked at so far, there's only been 1 cation. Now that won't always be the case. And in our next example, we're going to look at where there's multiple cations, multiple of the same cation. In this case, we are going to look at Mn3PO4 2. Now in this case, we see that this has Mn, and that is manganese. Manganese is number 25, and it's right in the transition metals. Now in this particular example, we have more than 1 manganese. We have 3 of them. It says Mn3. That means we have 3 manganese and 2, we're going to come over here and look, 2 phosphates. Now in this case, before we get to naming anything, we do need to figure out the charge on that transition metal, and we do have a little bit of an extra step here. Now in this case, I'm going to rewrite it out. We have Mn3PO4 2. Now that means we have 2 phosphates. Each phosphate is 3 minus. That means for both phosphates together, this entire half, or all the anions put together, is -6. Now because this is a neutral compound, our manganese half must be +6. Now in all the previous examples, we would have been done because they all had 1 cation, or 1 metal. In this case, we have 3. So the total of all 3 added together is 6. We can kind of think of this as x plus x plus x equals 6. Now the simplified way of saying this would be, instead of x plus x plus x, is 3x equals 6, with the x being the charge on the manganese. Well, we can divide both of these by 3 to solve for x. X equals 2. Our charge on our manganese is a 2+ charge. So the way that we name this is we go manganese 2 phosphate. And that is our name for this compound.